Hi, my name is Thomas Weible. I'm the co-founder of Flexoptix, the company which is specialized in optical transceivers, those tiny modules which have basically two ends. One end is the electrical side, which I don't want to talk today. That's our main job, but they also have an optical side. And there was a wish of the UKNOF community to have a comparison of the different type of plugs which have been used in the past and which are still, or which are upcoming now with 40 gig or 100 gig. And that's a talk today about. There is not much about fracking, but actually I got that picture in and I really liked it. It's an MPO plug, and someone mistreated this plug quite bad. I don't know how he made it, but he made it. But even worse, it was a colleague of mine. And yeah, but the QSFP plus where it plugged in was still working somehow. So I'm going to start with a small comparison, but before we jump in that topic, I give a rough overview how such a fiber optic plug looks like when you cut it in pieces. And then later on we look on the application level, especially when it comes to MPO plugs, what we should take in consideration using those plugs. So we got a fiber optic plug, and there are mainly 5 parts. So in the middle we got our fiber, it's going through the entire plug. We got the fiber coating or the cable around, that's the blue part. And then for sure we need a housing and for our fingers to hold the plug itself. And then the interesting part is inside, that's this purple thing, that's the ceramic ferrule, which actually holds the fiber itself. And the surface of that of the ceramic ferrule, that's the physical contact surface which is connected to the counterpart plug, and that's really important, which you will see later on. The spring inside in the housing is needed to put a little bit force on the ceramic ferrule that both plugged ends are physically connect to each other with a little bit force. Now, taking this one, in the past we got mainly 4 different type of plugs. For sure there are even more out there, but these are the most common ones. The first one is the SC one. Is a push-pull mechanism, and from the transceiver perspective you might have seen it on Xenpex or GBIX, the godfather of transceivers, the GBIC. And I have seen it quite often even in today's installation in house wiring, so it's a very, very handy one. It's a ruggedized plug. The other one, the ST, it's a twist-on mechanism. When you plug it in, you have to twist it. I have seen it mainly on multi-mode installations, but there are also single-mode applications as well. Very important, all plugs I'm going to show now, it doesn't matter which application you're going to target, it's multi-mode or single-mode, both can be used for both applications, doesn't matter. The third one, I was quite impressed to see that one. It's an E2000 multi-mode. It's the first time ever I see that one. Normally E2000, and what I've seen so far, the green housing used for single mode. The interesting part about E2000, first of all, it's patented by Diamond. It's expensive, and it got this nice dust cap in the front. Maybe I take that, hopefully. Here we go. That nice dust cap. It has 2 functions. First of all, when you plug in, or basically when you release the plug, it goes down, it covers the ceramic ferrule, it closes down the ferrule so no dirt and dust is coming on that ferrule where the light is going through. And the second one, which is important for high or for long distance transmission with high power, with amplifiers behind it with high light power, it's good for eye safety, so you don't have to worry about your eyes when you look at the plug because it's covered. But as I said, normally single mode and green housing. And the last one is the FC. I haven't seen it at all on regular transmission gear. I only have seen it on measurement equipment for single mode application, basically. It has also twist-on coupling ring, but it's not to twist, it's more like a nut. You really have to screw it to your device. All in common, all those plugs have that this ceramic ferrule has a 2.5 millimeter diameter, which is compared to the next ones quite big. And this comes to my favorite. It's the LC one. The LC, I'm pretty sure everyone is quite familiar with it. You can make a whole bunch of applications. That's a LC single mode. With a simplex one, you can have it as a duplex version. There are even things like this one, which I personally really like. Is I got here. Sorry, this was the plug and the microphone. It's looks like this. It's a one cable, but it's a duplex connector here, a duplex LC. It's called Uniboot or Uniboot. The good thing here is you have only one cable. There are 2 fibers in there. It's really handy. The bad thing is if you want to change and you want to play that game, you plug in the duplex fiber and your link doesn't come up. You have to swap it. You can't do that with that Uniboot. You really have to get the right patch course. With the regular ones, with 2 fiber cables, you can open them and change it. Big advantage, port density, definitely. Really great about LC duplex, and it's a really simple plug and massively used in these days in the applications out there or installations. The diameter of the ferrule is 1.25 millimeters. And finally, the last one is MPO. And there I have to stay a little bit, because first of all, the MPO, what does it stand for, the acronym MPO? MPO is multi-fiber push-on, and actually it's quite an old plug. It was developed in the 1990s by NTT AT. The main idea was having 12 or more fibers aligned in one ceramic ferrule and enable a plug with a multi-fiber plug. But there was no application so far for that high port density or fiber density actually. And in the last 3 to 4 years, when 40 gig and parallel transmission, 40 and now 100 gig with parallel transmission came up, this was the starting point when the multi-fiber push-on plugs got somehow famous. MPO is defined by IEC and TIA, and there is also another type of plug which is called the MTP. Where it does stand for the acronym, I have no idea. Maybe multi-fiber trademark plug, because it's patented by US Connect, a US-based company which improved basically the MPO connector in certain points, like the ceramic ferrule in front, which aligns all the fibers, which you see here on the bench down there. These are 12 of them. They have some patents on how they align the fibers, and especially also on that block of, it's a floating block of fibers that when you plug in, plug out, that it can move up and down, and US Connect improved that angle that you even wider than the standard defines. It's just one thing. On the website from US Connect you find quite the details. It is compatible to MPO, so you can plug in an MPO to an MTP, but bear in mind, since the start of the multi-fiber plugs, we have now 2 genders. So we get female and male plug. The previous ones, they didn't have any gender, so they were gender-free. The gender was done via the connector itself. Now here we have a connector to connect both plug types, and we got the male and the female. The male is quite obvious, and the female as well. The male got 2 sticks. Right. About density, we have 12 fibers in one row, and they can be in one ceramic block, can be up to 6 rows. So in total, 72 fibers in one plug. It's pretty dense. So every single fiber has a diameter of 0.125 millimeters. Okay, staying with the parallel transmission idea, coming now to the application level. Now, parallel transmission came up with 40 gig and 100 gig, especially straight out of a transceiver, for example. And when we come to the parallel transmission, we get a new issue coming in: polarity. What is the polarity thing? That's what I introduced before with the LC plug when you play that game, turning around the plugs. But within an MPO plug, you can't do that anymore, because they are all aligned, all fibers in one row. to change the polarity is quite difficult there. So what is the polarity? It's basically the alignment of the fibers comparing both ends. And we got mainly 3 types. We got type A, which is straight. We got type B, which is crossover. And back in those days where we had 100 megabit copper links and there was no auto negotiation and auto crossover, you also needed crossover cables there to link 2 devices like a switch. The same applies here. It's type B, that you have a crossover link type. And then we got pairwise crossover. Actually, this was the reason for us, although we're doing just the transceivers, looking on the cable stuff, because we got cases coming in where people wanted to connect back-to-back QSFP pluses with 40 gig, and their link didn't come up. And they complained to us and said, hey, the transceiver is not working, it is faulty. And we figured out, oh, they got the wrong patch cord. And they couldn't twist it or they couldn't turn it around. So they had a type A polarity, so they connected transmitter to transmitter and receiver to receiver, and this didn't work at all. So they needed a type B polarity plug, and wow, it worked. Looking on the top side, this is the receptacle of a QSFP plus. We have here 4 transmit lines, so it's fiber number 12 till 9, and the receiver side is 4 till 1. So they are lined next to each other, and therefore that's also the reason why we need type B here for getting a back-to-back connectivity between 2 transceivers. For sure, if I'm just talking about back-to-back connectivity, when you go or when you have a in-house wiring where you have patch panels and stuff like that, then you should really think about your polarity. So you can have that interesting game saying I have type B, type B, type B, ends up in type B. It's great because then the link is working. But if you have one time type 8 in there, you at least need one time type B as well, because otherwise it won't work. And this can be really a small mess when you need a patch cord which has a different polarity, because you don't see it from the outside. What is the polarity? You have to measure it or you mark it somehow. Parallel transmission has the effect that when we stick now to multi-mode, so we do, for example, in the 40 gig, we do 4 times 10 gig, even on the electrical side. So the electrical side is formed by 4 times 10 gig, and also on the optical side. For 100 gig, it's similar on the optical side for multi-mode. Really important here. We have 10 times 10 gig. On the electrical side, we have 4 times 25, a little bit different. So the transceiver does change the speed here and the lanes. Now, when we think about the 40 gig now, we stay to multi-mode. Looking in the IEEE standard, it defines, when we take an OM3 fiber, for example, it defines the maximum link distance should be 100 meters. Looking back to the old days of 10 gig, there the definition was 300 meters. What is the reason for that? There are mainly 3 influencing factors reducing the maximum link distance. So one is jitter, the other one is chromatic dispersion, and the third one is attenuation, especially the insertion loss of your plug. Skip this one. And so what does this mean? So imagine you're on the highway, and we take an example of the analog world, and it's always like this. The chromatic, when we go for the jitter and chromatic dispersion, it's about the signal delay propagation. So when your signal traverses the fiber path and your signal, imagine it's a car. When you have jitter, for example, you compare each other. You're doing a race on the highway with someone else, which you shouldn't do. It's not good. But if you would do it, if one car is faster than the other, this could be compared with jitter. The other one, looking at chromatic dispersion, is quite simple. You're driving at a certain speed level, and there's just at the moment there's a speed limit. You have to slow down. This is chromatic dispersion on the fiber path at the end of the day. And insertion loss, yeah, I don't have an example for the analog world, but It's, yeah. And now, looking for the 40 gig thing, there is also an interesting, there are some smart people out there doing stuff like this. We got here those nice interesting cables, look like this. So we got one MPO here, parallel transmission, 4 times 10 gig, and we got 4 LC duplex. And that's also the application for it. So we can break out a 40 gig transceiver up to 4 times 10 gig. That's pretty handy in terms of port density when you look at today's switches. So you get a whole bunch of 10 gig ports out of a 40 gig, and if you have a couple of 40 gigs, you get 4 times more 10 gig ports. Now, there are some really smart guys out there who take those cables for 40 gig links. So they have an old house wiring based on OM2 fiber, and the best would be an ST plug or an SC plug. They take here a QSFP plus doing 40 gig, plug it on their house wiring, split it up over 8 fibers, and on the other side, they take the same cable again and combine it again on their 40 gig. It works, it might work, but I don't want to troubleshoot it because it's a 40 gig interface, and if one tube or if one fiber path is failing, I don't want to troubleshoot that. That's pretty difficult to figure it out because the entire link will drop down. It's not that you're running on 30 gig, then you're running on 0 gig. And this is really, it can be really cause headache to troubleshoot that. So better, if you want to run 40 gig or 100 gig, you spend a little bit money on a new wiring here as well, because this is easier then. I skipped one slide, and this is the comic here, is when we go back to the plugs and done with the application level, there you might have seen these acronyms APC and UPC. And that's quite simple to explain. So it's about the angle of the plug itself, and why is it angled or why is it not angled. So APC stands for angled physical contact, and the UPC is ultra physical contact. The poor guy down there playing handball, when he throws the ball against the wall and the angle of incidence equals the angle of reflection, he will get it straight in his face. That's physics high school. Now, when he plays football and kicks the ball against the ball may go somewhere, because also again, angle of incidence equals angle of reflection. And that's the reason why there are plugs out there where the surface is angled, which you see on the top, the green one. It has an angle of 8 till 10 degrees. And what happens is the physical effect in the fiber, when the light hits the surface, it will not reflect back, because we don't want to have back reflection in our fiber. We always want to have the light going in one direction, not backwards to the transmitter. So we want to have as much as attenuation on the back reflection. Therefore, on long distance links and high power amplified links, mainly angled plugs are used. You can identify them on with the green housing, because the back reflection attenuation is up to 60 to 70 dBs. Looking at a straight plug, the older ones, which were only physical contact, at around 30 dBs back reflection attenuation, and then the latest, the newer ones, the ultra physical contacts, the UPC, it's around 50 dB. Housing color in single mode is mainly blue. And the MPO here, that's also an MPO, what I show here. It's just an example. You can get the angle type for all kind of plugs. It doesn't matter. It's just an example to see that also the MPO is available for single mode. Last but not least, which is still important, even though we got the nice, interesting plugs out there, is that you should clean it. Why? These are not pictures of a plug, these are the counterpart. These are all transceiver pictures. After a dirty plug was inserted into the transceiver. So starting from the left, I got this was a TOSA which didn't work at all anymore, because there was somehow dust or tiny rocks or sand or whatever on the ferrule itself. When they plugged it in, it didn't work, and when they released it, it looked like this. So a piece of the of the transceiver was broken. The second one in the middle I really like because I have no idea what it is, but it really looks impressive. It's even longer, so I cut the picture, but it's even longer. It looks like a metal piece. The link wasn't working either. Interestingly, after cleaning, it was working perfectly. And the third one, that's everyone has it. It's grease from your fingers. And the grease was not at the first time on the transceiver. It was first on the plug. And afterwards, it was plugged in. It was on the transceiver. And that's the result, how it looks like. Link was working. A little bit attenuation and ugly picture. All right. I forgot one thing, and I think that's worth to mention. I got what I mentioned before on the polarity about MPOs. When I showed that picture here, I said it's difficult to do it, to change the polarity from IE to B to B to A, but there is a way to do it. Talk to me later on. I got a tiny tool here, and I can show you how it works. So when you get stuck in a data center, you got the wrong MPO plug, there is still a possibility to do it. You need a little bit of force and some tools like a small screwdriver. I can show it to you later on. Just talk to me. Okay. Right. So this was my overview about the plugs. Thank you very much for listening. 2 words about the final thing about the Flexoptix. We are pretty excited, the entire crew of us. We are now 30 people, so are really excited in the development team, launching 2 new products in the middle of the summer somehow. We keep on rocking and we keep you updated on those ones. Thank you very much. Do you have questions?
Any questions? Adrian.
Hi. The one thing I don't really understand is surely when they designed these plugs, they could have said, you know, these connectors are transmit and these receive, and it's just defined, and you never need special cables or plugs. They're always light comes out on the left and goes in on the right or something. Why is there such a confusion over polarity?
Okay. There is actually no standard, but there is a little bit, I take that slide, a thumb of rule. Basically, when you look in front of a transceiver, the transmitter is always on the left side, always, okay? For sure, when you turn it around, it's on the right side. But it's always on the left side. Now, in terms of the plugs, the problem is the wiring in a building. If you have a back-to-back connectivity, that's not an issue at all. Then you could have that rule saying you need always type B polarity because you need crossover in fiber optic ways, and take always the same type of plugs and the alignment. But as you have the wiring in a house, you need how to explain it? There's a lot of freedom to set that up. Does this answer the question?
Okay.
Okay.
Okay, thank you
Perfect.
very much, Thomas.
Right.